All right, start of a new unit, and that unit is momentum. Momentum is a quantity that is conserved like energy, not conserved in the exact same situations, but very useful in collisions and explosions. Momentum is letter a lowercase p. It is a vector, which is a huge difference between it and energy. So momentum equals mv. The momentum vector, of course, is in the same direction as the velocity vector. Um, Again, like I said, it's useful in collisions and explosions. If you have one of those events happen, you really are going to think about momentum. The reason momentum is conserved is because there are no external forces on the system during the collision or explosion. And because of that, that means there's no change in momentum for the system. Again, individual objects will have increases or decreases in momentum, but the net change on the system will be zero. The only way you can change the momentum of the system is to have an external force like friction or gravity act on the object or the system, and then you can increase or decrease the momentum of the system. But a collision and an explosion will always have a net force of zero or an external force of zero. Thus, we're going to say the momentum before the collision and the momentum after the collision are equal. Very similar how we said like energy was equal here and there. There are different types of collisions. The standard collision is just inelastic. If they describe it as sticking together after the collision or completely inelastic, that just means that the objects travel with one velocity after the collision because they basically fuse together and become one object. If they say the collision is elastic, then we actually have an additional quantity that's conserved and we conserve energy. Elastic like rarely happens. That's kind of like we close our eyes and just kind of pretend it's elastic. It's like a bouncy ball bouncing off the ground. Does it really bounce up to this exact same height? No, it's going to lose energy in the collision because most collisions are inelastic and they lose energy. Things that stick together lose tons of energy, like 97, 98% of the energy might be lost in the collision. However, if they tell you a collision is elastic, that provides an additional quantity that we also can conserve being energy. However, all types of collisions conserve momentum. So it doesn't matter if you don't know the type of collision. You're like, ooh, I don't know. Is that elastic, inelastic? It doesn't matter. Conserve momentum because momentum is conserved in all collisions. I'm going to take you through some examples and some typical questions that might be asked. I know this video is long, but this is the introduction to momentum. This is 1D collisions, so just one-dimensional collisions. There's another video for 2D, and there is a video when we actually do have an external force and we have a thrust, like a thrust or an impulse on the system. But all of these are going to be P1 equal P2 situations. Okay, so first situation is we just have a box of M1 traveling at V0, hitting another box at rest M2. So I gave you the masses, I gave you the initial velocity, and I say find the velocity and decide how much energy was lost. Okay, let's say for this one, I believe, yes, I do. Let's say this one actually sticks. I didn't write that down, but I did mean that. So we are going to say that they stick together afterwards. Okay, so we say P1 equals P2. The momentum before the collision is just M1 V0. Remember, momentum is just mv. We only have to worry about the x direction, even though I know it's a vector, because there is only one direction. So lots of times we don't even write x hat if it's only in one dimension. But the original momentum of the system is just m1. m2 isn't moving. It doesn't have any momentum yet. And afterwards, since they stick together, they basically fuse together and become one mass. So then that mass travels at some final velocity. Okay, so this is just 4 times 12 equals 4 plus sticking to another 2. So what's this? 48 equals 6 times VF. 48 divided by 6 is 8. So afterwards, they'd be traveling at 8 meters per second. Okay, so it says find the final velocity of the system, and then let's decide how much energy was lost in the collision. Maybe we didn't lose any energy. I don't know. Let's decide. Certainly, if we stuck together, we're going to lose energy. So let's compare the original energy. We'll call E1. The original energy is just 1/2 m1 v0 squared. Okay, So that's going to be 1/2 times 4 times 12 squared. And we get 1/2 times 12 is 288. 288 joules. Okay, and then E2, meaning afterwards, we have 1/2 M1 V final. And we probably could have wrote these together considering they are traveling as one mass, but right, that's the same thing as just saying 1/2 of M1 plus M2. Algebraically, of course, those are equivalent. Probably easier to plug it in that way. So that's 1/2 times 6 times 8 squared. And we get 182. Okay, so we had 288 joules, and now we only have 192 joules, so we must have lost 96 joules of energy in that collision, which is typical for collisions. Heat is going to be created, we're going to lose energy. However, momentum is conserved because momentum is conserved as long as there's no external forces, and there's no external forces in collisions and explosions. Okay, so that's kind of the start. Okay, next one. Okay. Okay, this one says, same situation. A lot of them are like this, right? M1 is moving at some V naught, hitting M2. I give you the quantities, except now I tell you it's given that M1 rebounds at V naught over 2. Let's find V2, and then let's classify the collision as some sort of type. Certainly they don't stick together because I tell you M1 rebounds. But we're going to conserve momentum, so P1 equals P2. M1 V naught equals M1 V1 plus M2 V2. Okay? So they're both traveling with their own momentum after the collision. Momentum is a vector, as a reminder. So we're going to say 2 times 12 equals 2 times, it's rebounding, meaning it's going to go that way afterwards. Since it's a vector, I got to use a -6 plus 6 times some unknown V2. So this is 24 equals -12 plus 6. Add that over to get 36. 36 and 6 make 6. So V2 apparently is 6 meters per second. So V2 is going to be traveling at 6 meters per second after the collision. Okay, so classifying the collision. Maybe, just maybe, this turned out to be elastic. Let's figure out. The energy at the beginning is 1/2 M1 times V naught squared. That's 144 joules, right? 1/2 of 2 is just 1, and then 12 squared is 144. The energy after the collision is both of them. Now, does it matter that one's moving left? Of course not. Energy is a vector. It gets squared anyways. So we have 1/2 of 2 times 6 squared plus 1/2 of 6 times 6 squared. So 1/2 times 2 times 6 squared, of course, well, that's just 36. That was silly to use a calculator for. And then this is 1/2 of 6, which is 3, and 3 times 36, of course, is 108. And that is 144 joules. So what type of collision must this have been? You're like, oh, look at that. Energy was also conserved. This must have been good old elastic. So this must have been like a really good bouncy ball against a really good bouncy ball, or maybe this one had a magnet on it, and then this one had a magnet on this end, and when they hit, they actually never touched and they just repelled each other or something, and energy was also conserved. Of course, momentum was conserved, but in this case, we showed that energy was also conserved, which means we can classify it as elastic. Okay, this one's going to be a little more intense. Algebraically, what's going to happen here. So I give you M1 and M2, except this time M2 is also moving to the left at some speed, again moving left, and then it's given that I lost a particular amount of energy, and I want to actually be able to find V1 and V2. Ooh, this is going to be pretty intense. Okay, so P1 equals P2 for sure. So I guess I can go in the abstract. M1 V naught minus M2 V naught over 2. Again, I put a subtraction there because I know it's moving left. Afterwards, I have no idea what's going on, so it's just M1 V1 plus M2 V2. Okay? let's put in some numbers now. So this is 2 times 12 minus 5 times 6 equals 2v1 plus 5v2. So 24 minus 30, what is this? So negative 6 equals 2v1 plus 5v2. Okay, now the energy lost. All right, E1 is equal to 1/2 M1 V naught squared plus 1/2 M2 V naught over 2 squared. Okay, that gets a little messy, but we know the numbers. 1/2 times 2 times 12 squared plus 1/2 times 5 times 6 squared. Okay, so 234 joules. Okay, if we lost 160 joules, we can subtract 160 and get 74 joules of energy is left. Okay, so here's where we're going to get another equation. E2 left. Oh, that has to equal E2 actually, right? But E2 as a variable equals 1/2 times 2 times V1 squared plus 1/2 times 5 times V2 squared. So what we end up saying is that 74 equals 1/2 of 2, that's just V1 squared, and this is just 2.5 V2 squared. Okay, so what I've done is I've used this and I've got that guy and that guy. I have two equations and two variables, and I just have to solve however you want to do it. Okay, so I don't think I actually wrote this down yet. Maybe I just made this problem up on the spot. So let's take, what's probably the easiest? Let's take this equation and solve it for V1. So V1, if I leave V1 there, I'm going to get a negative 6, I'm going to minus 5V2, and I'm going to divide that bad boy by 2. That's equal to V1. And I'm going to take that and I'm going to chuck it in over here. So 74 equals negative 6 minus 5V2 over 2 squared plus 2.5 V2 squared. Oh, that's gross. But you know what? I have one variable and one equation. I'm going to bust out my calculator. Let's see if we can do this. So this is 74 equals negative 6 minus 5x. Okay. I'm going to divide all that by 2. Actually, I'm going to square this. Squared, and I'm going to divide by 4. It's just going to be easier to do that. And then plus 2.5 x squared. I'm going to set my window so I can make sure I get all the way up to 74. And maybe my x is, I don't know, maybe up to 20. Let's graph it. Hopefully I get some reasonable answer. So second calc, let's do the intersection. Again, you can be doing this with me if you really wanted to, or you can fast forward till I'm actually at an answer. Boom, boom, boom. I'm going to get 2. Look at that. V2 equals 2. Well, that was easy. Okay, so then if V2 equals 2, I can find V1. So then this is negative 6 minus 5 times 2 over 2. That's negative 16 over 2, which means it's negative 8, which just predicts that when they hit and collide, the M1 is going to go that way. So this is going to be going left at 8 meters per second, and this is going to be going right. Okay, you got all that? So that had an example where the algebra got a little intense, because giving you this information allowed me to give you another equation, which allowed me to give 2 variables, where lots of the time you only have 1 variable, like what is just V2. Okay? All right, one more. I know the video was long, but it is the introduction to momentum, so there's a lot of things kind of to talk about. All right, this one is a fun one. This one is the ballistic pendulum. Okay, so this is like a gun firing a bullet and it lodging into this thing, or it could bounce off that thing, or it could slice through. Okay, this ballistic pendulum, I'm going to fire a bullet of mass m1 at speed v0, and it's going to hit m2, and it's going to create a hole right through m2, and it's going to keep going at v0. But then what's going to happen, m2 is going to get a little momentum from that collision, and it's going to swing up. I want to know how fast m2 is going after the collision, v2, and the maximum angle the rope makes with the vertical. All right, first, it's a collision, so conserve momentum. Momentum at the beginning is just m1 v0. Nothing else is moving afterwards. m1 is still traveling at v0 over 2. And again, this is a positive because it sliced through. If it rebounded, it'd have to be a negative there. Plus, m2 is going to get some velocity. But these are all just known quantities. 1 traveling at 80, 1 traveling at 40, and then how fast is 10 going to slide up. So this is just 80, 40, so this is just subtracting, and I get 40, and you're like, okay, the box is going to, after the collision, m2 is going to go to the right at 4 meters per second squared. We could find the energy lost in that if we wanted to, but we kind of already did that question. Now, this is the collision. And this is what the AP loves to do. Now, I want to do the swing. The swing is not momentum. The swing is energy. Okay? Think. Box 2 is there, and it's got a whole lot of kinetic energy after the collision. And then it's going to swing up. Oh, that's not how it's going to be attached. It doesn't matter. My picture's kind of silly. It's not going to maybe look like that, but who cares? Then it's going to swing up. And I want to know this particular angle. Okay? So in general, you're like, oh, this is so easy. The kinetic energy after the collision is just 1/2 m2 v final squared. That's how much energy m2 has after the collision, and that energy does convert to m2 gh. Okay, check that out. I don't even need the masses. 1/2 times 4 squared equals 9.8 times some height. All right, let's find that height. So this is just 8 divided by 9.8. Oh, buddy. 8 divided by 9.8, and you're like, okay, it's going to swing up to 0.816 meters. Now, all I have to do is a little geometry, okay? So, if the length of the wire or string is 3 meters, if that's 3 meters, then what angle will that make? So just think about this. We're going to use this a lot. There's it at the bottom, and there is it here. We're going to make this triangle. That's the height change. This length is L. This length is L. This is some theta. This length is L cosine theta. Okay? So from here to here is L cosine theta. This is the actual height change during the swing. So what is H? H equals the total L minus L cosine theta. Hopefully that makes sense. It's just some easy subtraction. The whole thing is L, and this is L cosine theta, so H equals this. So what we have here is we have 0.186 equals 3 minus 3 cosine theta. Let's just do some algebra here. So move that over and then subtract. So it's going to be 3 minus 0.816. Enter, divide by 3, and then let's take inverse cosine of that, and we get an angle of 43.3 degrees. Okay, so that's the ballistic pendulum. We're going to fire a bullet into something, and again, it could stick. It could rebound. If it rebounded, that would have to be a negative. And in this case, I told you that it slices through and only loses half of its velocity. That gave me enough information to find the velocity of the block afterwards, with the block afterwards. Then it becomes an energy situation in which the kinetic energy becomes potential energy. And then I have a little geometry here where I now know that on these swing problems, the height change is going to be L minus L cosine theta. You will need this in class. When you do the one-dimensional book questions, you are going to have to either derive yourself. You can look. I derived them probably in class. There is a video of me talking about the derivation. There's a PDF where you can just read the derivation. But there is a situation where you have M1 traveling at V0 hitting M2. And if it's elastic, meaning if you're told the collision is elastic, you'll know that you can conserve energy. And what pops out of that conservation of energy and momentum are these equations. And so you know V1 and V2 represents the velocities of these two objects after an elastic collision, and this predicts exactly what they'll be. And again, you're going to need these when you do the book questions. But again, you should watch an additional video, talking about the elastic derivation.